More than 30 people were injured as a large tidal bore crashed with great force into the bank of a river near the city of Haining in China. Given extra impetus by a typhoon, the huge and powerful tidal wave gathered momentum with alarming speed. People were heard screaming and many ran for cover.
Bit late maybe for us because we talked about waves a couple of weeks ago now, but tidal bores are things that happen from high tides in river mouths of a particular geometry and come up as a solitary wave to invade the estuary, and can be quite violent. They occur in a place like Fundy, Bay of Fundy, which is between Nova Scotia and the rest of Western Canada, the Severn Estuary in Western England as well.
Getting wave after wave, whereas here in China on the Silver Dragon, there's one wave, and it's once a year. So you really have to be ready and have your team
It's
be ready
water related,
and
you can
go
see.
with the flow, and you just hope you get a little bit of the Silver Dragon.
I think with this event on every year, it's just going to grow and grow. And surfing in China will eventually become.
I don't know if Penn State has a sailing club. Does anyone sail? Dinghies like this? So you're familiar with this activity. Used to be Penn State had boats to rent at Stone Valley. I don't think they do that anymore.
Royal Air Force No. 617 Squadron attacked German dams in Operation Chastise, otherwise known as the Dam Buster Raids.
Nazi German dams, in case we have
617 Squadron was formed specifically to attack 3 major dams that provided hydroelectric power and water to the Ruhr Valley, an area of enormous industrial significance to Germany. Operation Chastise was developed with the intention of destroying the dams and depriving the German war effort of the Ruhr's potential output. The operation was developed in such secrecy that, with just 2 nights to go until the night of the attack, only Wing Commander Guy Gibson and a small number of key officers even knew the intended targets. Despite being just 24 years old, Gibson had already flown over 170 missions and had been specifically chosen to lead 617 Squadron. The destruction of the dams depended on the correct deployment of a new explosive that had been invented by Barnes Wallis, the assistant chief designer at Vickers Aircraft Factory. Nicknamed the Bouncing Bomb, he created a cylindrical bomb that would be spun backwards at a speed of 500 revolutions per minute before being dropped onto water from a precise height at a precise speed. The bomb would then bounce over the torpedo nets installed in the dam's reservoirs before spinning down the dam wall and exploding. The squadron began their mission from RAF Scampton on the evening of 16th of May. Arriving at their targets in the early hours of the 17th, they breached 2 of the dams and lightly damaged the 3rd. 8 of the aircraft were shot down during the mission, and 53 airmen were killed.
Okay, it's probably about time to get going. And so the first few things we already looked at. Clearly there's the relevance to these. Maybe it's worthwhile just recapping to be able to make the case for the relevance of those kind of initial forays into what we're talking about. We're talking about pressures on structures. And so we can probably use those to illustrate the points of what we're interested in. So in the first case, this upside down boat has a sail attached to it, which is a plane, a centerboard, someone standing on here, reefing on this to pull it up. And so clearly the relevance to this class is that if you look, for instance, at the pressure distribution that is applied on this, on the sail, of course the sail can kind of move around a little bit, but the pressure distribution that's applied on the sail is something that you have to pull it against to be able to write it. And so really it kind of embodies all of the main points that we talked about last time, and that is that there's a pressure distribution which we can define because this is equal to the pressure at any point is equal to gamma h in this particular case, as this is the depth. We know that we can get the magnitude of this resultant force that acts here, and this is always equal to the area that it's applied on, the depth of the centroid, and the unit weight of the fluid, which is water in this case. And as a special case of this last time, we also talked about the location. Is this off the screen? Sorry about that. We can also talk about the location of where this occurs. If this is h, then this depth to the centroid is what we called y sub r. Not a very good y. And in our particular case, y sub r was equal to 2/3 of h in this particular case. hc is the depth of the centroid, which is equal to the height over 2. And so we have enough there to be able to calculate from that the sum of the moments are equal to 0. And so in other words, this lever arm here, is that on the screen or off? Oh, it's off the screen. This lever arm here, L, and the reaction by the person. So we know that R times L has to equal FR times Y sub R. So that's kind of really what we're trying to do in a very simplistic way. And so that kind of embodies the three things that we talked about last time that we need to be able to do. Is that the first, we need to get the force magnitude. And that is, in a generic case, the unit weight of fluid, the area that it acts on, and the depth of the centroid of the plate. We need to be able to find out where it acts. Which we call YR, the location of the resultant, and it's relative to it can be relative to any particular location, typically relative to the surface of the water, which we developed an expression for last time, which was this, but it's not, we said it wasn't generic, and so we'll go revisit that today. And the other point is that we, what I call define a failure mode. And you might remember that we got this point of action by taking moments. It could be around any point. It could have been around the bottom of the sail, or it could be around the top of the, well, I guess that's the top of the, well, it's upside down. The top of the mast or the base of the mast. You could take moments around either one and come up with this expression. But explicitly, if you want to know whether you can right the boat, then the moments that you have to take have to be around the rotation point that you're looking at. And that's the last thing. And so only this will give you the force that you have to apply to be able to write it. If you're crouching down and your lever arm is small, you need more force. If you're tall and you're higher up, then, or the centerboard is taller, then you have more leverage on it. And so that's kind of the generic things that we're looking at. So that's what we'll try and talk about today. So two things maybe today. We'll do some examples, but we'll talk generically about how we get this point of action, and we'll do some examples with different failure modes to represent these behaviors. Let's see where we are. Okay, so I'll go back to this. Hopefully you can see much of this. Oh, jeez. Good enough. So those are the things that we've said already. We've made this point that we know how to get the forces. This is generic. Maybe always true. If we have forces in the x and y directions, we can always get the resultant of them. I guess these are horizontal and vertical. We can always get the resultant of them from Pythagoras, which is merely what that is. And the one thing that we haven't yet done is we haven't figured out exactly where this center of pressure is generically. We could derive it, and I think there's a derivation that's right here that we could go through, but I'm not sure that that's particularly useful. But it is useful to maybe to look at it in kind of overview. And this little page of relationships kind of does that specifically. And so it just goes through, makes the case that how we got this force that acts is that we take an individual piece where we can define the pressure, and we isolate that force as being this area under the pressure distribution, and we just multiply it through by this width across the top of here. And so we end up with a prism that goes across here, and I guess comes out here like this. Actually, that's not a bad drawing. That's not perfect. And so this area under here is what we're attempting to do. We're taking a pressure, we're multiplying it by an area, which is a width, and a component, which is dy. And we just sum up all of these individual components. That's what we're doing. That's all an integration is. And if we do that, we end up with this expression here. It includes the unit weight of water because pressure is equal to unit weight times y in this particular case, and we end up with this expression here. We also know that we can make sure that if we can calculate what the magnitude of this average force is, Fr, and we know the lever arm through which this force acts, which is Yr, then that has to be the same as a moment that's applied to this. And so this expression here also has to be true. And so if we can calculate what the individual moments are for this independently of this equation, and of course the way to do that would be to think of this as being our individual force that's applied here. We can calculate exactly what the magnitude of that force would be, which is equal to the pressure at that point multiplied by dA. And if we multiply that through by the lever arm, which is y, then the product of y times p dA gives us the moment, that little segment. So not only can we get it for that one segment, but we can do it for everything else. So we can define the moment just the same as this pressure times area, but pre-multiplied by a lever arm, which is y. Okay? And so the idea is that if we can independently calculate this moment around here due to all of these individual forces that are acting at each point here, we end up being able to calculate what the moment is. And if we do that, we end up with an expression that looks like this. And so now we know what the resultant force is because we can calculate it, and we have calculated it. We know what the moment is independently because we've done that also. So if we solve for the unknown, which is this length, then we just look at the ratio of these two terms here. And so if we use the moment divided by the force, the moment is this term here on the top, the force is this term here on the bottom, and they're very similar to each other. The unit weights cancel out, the widths cancel out, and these integrals have to be done. So this is going to be a third y cubed, this is going to be a half y squared, and we end up with a generic representation in this particular case for the depth of the center of pressure, the point where that force acts. And it's an entirely generic expression. It doesn't have to be that the distribution passes to the free surface of the water. It can be a plate that's completely submerged. And so this term on the top, well, if you do this integration, you end up with a relationship which is this. This ends up being a second moment of area, as you could imagine, y squared. And we can use what's called the parallel axes theorem to be able to modify it. So it's a second moment of area, not about the x-axis, which sits on the surface, but relative to the centroid, which is this c. And so the easiest way to think about this is we end up with the point of action of this force, and it's equal to this center of moment of inertia, of area, about the centroid, divided by the area times the y-coordinate of the centroid, and plus the y-coordinate of the centroid. So all I'm doing is just dividing this through by this term here. And this is entirely general. It's an equation that you'll use throughout this session. Didn't need to belabor you'll never have to drive it, but you should know how to use it. And physically, what it's saying on this particular diagram is that if you have a plate which is given by these, by this outline here, maybe I can do it with a bigger, where's my width? So if you have a plate which is outlined here, and you know the depth of the centroid below the surface. I could probably have drawn this out myself better. And the coordinate system that we're going to use is one that now has this x-axis sitting physically on the top of the surface. So the thumb is the x-axis, sits on the water top, and the y-axis can be oriented any way relative to that. And the y-axis has to go through, so the xy plane, if you like, contains this plane itself. The upper limits are y1 and y2. And the slope distance, if you like, or the y-coordinate of that particular point here is y sub c. And that particular point is the centroid of the plate. So the centroid of the plate is just, if you like, the balance point. Did it last time, right? I could do it with this. If I balance this on my finger, that's the centroid of this plate as it sits here. And the center of pressure, in other words, where the force will act, which is the resultant force. Don't know if I can draw it very well. I'll draw it. This is the resultant. The resultant force is going to be equal to unit weight of fluid, the area of this plate, and the height of the centroid, which is this term here, vertical depth, because it relies on the average pressure at that point. The point where this acts is equal to yc plus some small amount here, which we'll call delta yc. So in other words, this length here would be delta y sub c. And so the whole length, if I draw it in red, because it's an important thing, this whole length here is going to be what we'll call y sub r. Right? And now these two expressions that we have here, this one always was generic. We said we could always use this. That's always true. It relates to the depth of the centroid of this plate. The net force acts at the center of pressure. Which is at this point here. Right? So it's very important to make that distinction. So with these these two pieces of information, we now have the ability to calculate what the forces are and their point of action on any flat plate, any orientation, horizontal, vertical, intersecting the surface or not intersecting the surface. And so maybe the best way to consummate this is perhaps just to do an example of which we have a number. Okay? What I didn't say probably is that these are standard terms. This is the second moment of area about the x-axis relative to the centroid. It's kind of a long term. And if you look in your book or if you look in these notes, you'll find it somewhere right here. So for a plate, it's equal to this. It's a function of the edge dimensions of the plate. And so this is the one that typically you'll use. And so it's just a number that you'd use relative to a plate that looks like this, which is B in width and A in height, that might have the water anywhere relative to that. Or for a circular plate. The first example we do is for a circular plate. And so again, the water is here. If you wanted to draw the coordinate system we had, this would be the x-axis, which sits on the surface. This would be the y-axis, which would go through it. In our particular example, it's a vertical saucer, if you like. And this is the... Didn't do it. This is the centroid. So this is the... this would be the height of the centroid in our particular case. Someone's on fire. And we're probably going to find, since the depth where it acts is always equal to YC, this is going to be YC, which in this case is the same as this, but we're saying that it acts at a point which is below it by some amount. And so this is what we would call, I suppose, delta YC, the extra part. And it's always going to be below the centroid for reasons that we may talk about later. Okay? So these are standard results. And so the standard result that we'll use here is that this second moment of area about the x-axis relative to the centroid is pi r to the 4 over 4. And I suppose the other thing that we'd note, well, fine, we'll talk about the other thing later. Okay? So this is a term that we're probably going to want to use. And so you'll see this result here. It's a pretty straightforward question. The idea is, I guess they're all straightforward when you've seen them multiple years as I have, but maybe not the first time. So we have a gate here. If there's a picture of a gate, they have it. It's a side view. And so the idea is that you have a gate which is circular. It has a pivot right here. We think, from what I just said, that the resultant is going to be below the centroid, which is the pivot. And so if the net force acts here, then it's trying to push it counterclockwise. And so the question basically is, what kind of force do you have to apply here to stop it from rotating? Just a simple moment force. We don't need to know that to be able to calculate the magnitude of the force or where it acts, but that's ultimately where we're going with this. So the question is, what's the magnitude of the force and where does it act? This is the plate. The center of the plate is 10 meters below the surface. The plate diameter is 10 meters, so the radius is 5 meters. So the centroid is right in the middle, which would be a depth of 10 meters below the surface. That means that this is also what we would call H sub c. And I guess we'd also call this Y sub c, because the plate's vertical. Right? If the plate was inclined, then H sub c would be a smaller number, and Y sub c would be a larger number off to the side. So we know the centroid of the plate, and we know its depth. The center of pressure, we can calculate. It's equal to this expression here. We said, I think before, that this is equal to pi r to the 4 over 4. should always have these dimensions of length to the power 4, divided by yc, which is 10 meters, and divided by the area, which is pi r squared, I guess. And so if you make those substitutions, this here is IXC. This is the depth of the centroid, which we said above is 10 meters. And the area is pi r, not on this figure, but pi r squared. So those are the individual terms. And also, we add this amount to it. Go through the math by substituting the numbers into this. This is yc, this is r squared over 4. The pi's cancel out, I guess. And yc is 10. And so it ends up being 10 plus 25 over 40, which is 10.6, 10.62. And that corresponds to exactly what we surmised, and that is that the point where this acts is not at the centroid, but it's some small amount below that, which is equal to 0.62 meters. And so that's the amount. So this is the delta, what we called delta yc. Y. Actually, which is equal to YR. Right? So that's where it acts. We can also do the same thing relative to, we haven't really talked about it, but you can see just by inspection, if you look at this plate, and if you go across this plate and look at how pressures change as you go horizontally, even if the plate's inclined or vertical, as you go across horizontally, the pressures are going to be uniform. And so it's not like going down in the fluid where pressures increase, and that's the reason that we have this discrepancy between the centroid of the plate and the center of pressure. If you go around here, and if you took moments around this vertical axis, you'd find out that the forces acting on the right side of this plate would be exactly countered by the forces on the left side of this plate if you use the central axis. So it basically means that the centroid of the plate is in the middle, and there's no net rotation around it. And this is the expression that we can use to define that. Don't worry about it, not so important. We have the point of action. We can calculate the magnitude of it. We said it's equal to unit weight of water, area of the plate, which we know, and the depth of the centroid of the plate. The 10 meter diameter plate is 5 meters below the surface, so the depth of the centroid is 10 meters. Which is this. And we have a magnitude of the force that acts, which is this, if you go through the math. So we've done two things. We say we want to do three things. Magnitude of the force, Fr equals gamma A H sub C. The location of where it acts, Y sub R, is equal to the depth of the centroid, YC, plus delta YC, which is this slightly complicated expression, but not too bad. Yeah.
How did you get IXC equals that expression if you scroll up just a little bit more?
Pi r squared.
Pi r to the 4th over 4 for IXC.
Okay. Standard result.
Okay.
From here.
All right,
So you'll use this table. So it's standard result. So it's worthwhile knowing. That's where it comes from. Right? Good. Shout. That's fine. So we said we've got two things. Magnitude of the force, point of action. If we want to define some kind of behavior, like righting the boat, we have to define a failure mode. And so for the failure mode for this, we're going to look at rotating it around this point. So what we can do is we can sum moments around here, and they have to equal 0. And so it's worthwhile making the point that to get those forces and the points of action, we could do it from first principles by taking moments, and we could do it around any point we choose, and we'd always come up with the same result. If we're looking at a failure mode, there is only one point to take moments about to do it. And so that's an important point to come up. So now if we take moments, then it's going to be something like Fr multiplied by the lever arm R has to equal resistance times L. No, I don't want to use R, do I? But I'll do that. So what do we know and what don't we know? We certainly know that L is equal to 5 meters. Right? Pivot in the middle, 5 meter diameter plate. We certainly know that this LR is equal to not 10.62 but 0.62 meters. It's just the distance between here. So this here is L sub R. And we definitely know that this force is equal to 7,700 kilonewtons. And so the only thing we don't know is the reaction. And if we go through the math, we end up... Okay, let me back off. Right now, with water on both sides, the force acting horizontally is exactly the same as the force acting left to right and right to left, okay? Because they're both acting on the same thing. If you drain this side, then clearly that's not the case, and you have this condition here. And so I guess that's what I was solving up here, and that is that certainly if you have this acting here and this acting here, there's no moment and the gate stays shut. It'd stay in exactly the same position it is without any backstop to it. But if you drain the right-hand side, clearly there's a mismatch because you have pressures acting on this upstream side, which will look like this, and zero pressure acting on the other downstream side. The relative point of action of this is below the pivot point, and so there's a moment that's applied. So this moment of FR times L, what we call LR, has to equal F shut times this length here. And this was the overbar. Okay? And if you go through the math, you end up calculating that the force to keep it shut is much less than 7,700 kilonewtons because you've got a long lever arm there. You could surmise that that's the case, right? Just from looking at the geometry. In fact, the magnitudes of the forces should be in the ratio of 0.62 over 5, right? The ratio of these two lengths, which is this. Okay? So the point is, and hopefully we've made it, that this is an absolutely generic expression that you can use for a flat plate. Only for a flat plate. If it's curved, I don't have anything curved here to show you, curved surface, you can't. But you can always use it for a flat plate. And that flat plate can be below the surface, it can be any shape, and the two important things to pull out of it are that you need to be able to define for that plate the centroid, which is again a standard result on that sheet we just looked at for the IXC terms. And physically what it is the balance point of a surface, if you're able to do that. I don't know not too bad, right? That is the centroid of that plate. But the force acts at the center of pressure. And the center of pressure is offset from that balance point by some amount which is, we've called it delta YC. YC is the depth of the centroid, slope depth of the centroid. Delta YC is the point below that where the resultant F sub R acts. And it's sometimes it could be offset. It might not be in the same line as that, and it depends on the shape of the plate. For most regular shapes that we deal with, we can also calculate how it is, where it is, by taking moments about the y-axis. And so if you took moments if you use the y-axis as the rotational axis here, and take moments of the forces applied on this plate as you go further away from the plate, you can calculate the location of the center of pressure, which might be offset a small amount to the left or right of this centroid. And you can do it by, again, using a standard result with these individual terms which we've already just used. This is x sub c, So in other words, it's offset by some amount to the left. This would be delta xc. This term here is what we've called delta yc. And so this term here, in this particular case, this length here is delta xc. Rare that you'd need to use that. Things just get too complicated when you use shapes that really aren't symmetric for this class. All right? Okay, so that's kind of the hallmark of what we'll attempt to do. So let's do some other examples. Same kind of deal. And actually you'll see that we can solve things in a variety of different ways. But this is, again, is one from the book. Same idea. So you have a hinge, which is a pivot. We want to be able to calculate if we have water held behind this gate, what force do we have to apply in this direction, P? Might as well make it big. What force do we have to apply in this direction to keep it from moving? And so if we think about this, we could imagine that we could represent it as a system that has a couple of different components, right? There are two faces, so we're not just dealing with one face now. And we know that we'd have some kind of pressure distribution on this plate that looks like this, which I'm not going to draw there, but I'm going to draw slightly differently as this because it just gets easier. And so in other words, we have a pressure acting on this face, pushing this plate in this direction, and I just want to draw it here just because it's easier for me to do that. And we also have a pressure acting along this base, which again I could draw as being this, but instead, just to make it different, I'm going to draw it down below. And so you can imagine that what we might want to figure out is what is the magnitude of this horizontal force, and relative to this, where does it act? And also, what is the magnitude of this vertical force? And also relative to this coordinate here, I'll call it LR, because it's not really, but it is kind of a YR. Or maybe I'll call it Y. Maybe I'll call it YR V for vertical, right? So clearly, if we have this, if we're summing moments, if we have all of those terms, we can write that P multiplied by L. Am I still on the page? No? It is on the page. Yeah, it must be. It is on. Yeah, it is on the page. So P times L. So in other words, this force here times this lever arm has to be able to resist horizontal force multiplied by YRH. And also the other counterclockwise force would be this FV multiplied through by YRV. Right? So of these, we definitely know what L is. L is equal to 4 meters. We don't know what P is. And we should be able to calculate what each of these are from what we've said before. Right? So, well, you have those values there. I'll make it smaller so you can see them. Won't go through the numbers. So the horizontal force. This is force 1. Just make sure, yeah. So the magnitude of the force is going to be equal to this. I'll change colors so you can actually see what's going on. So force 1 is going to be equal to what? Is F1 on there? Unit weight of water, the depth of the centroid multiplied by area 1. Depth of the centroid is what? 3 meters. The balance point of this plane is going to be this. So it's going to be 2 meters down it. So this should be 7 meters. And the area is going to be 4 meters, and it's something like 3 meters into the page. So this is going to be 4 meters times 3 meters. Just the area of this gate, nothing more. 7 meters, I can't add, can I? And you didn't correct me. So 3 meters plus 4 over 2 is actually 5 meters. Which is this. And if you go through the math, we can calculate the magnitude of force. The force acting here acts on this surface. It's actually also very easy to add. On this surface, the centroid has to be in this plane. So we know the depth of the centroid has to be 7 in this case. We know the area is going to be 2 meters times 3 meters into the board, which is 6 meters. And therefore, we have a magnitude of this force, which is here. These two forces. We have what I've called FRH and FRV, for those magnitudes. And now we need to work out where they act. This one's pretty easy, because we know that just by the symmetry, it has to act. There's no pressure distribution as you go, change in pressure as you go across it. And so clearly the depth, the location where it acts is in the middle of this plate. So that's straightforward to get. And the other one's a bit more challenging, right? We need to use this parallel axes theorem. So we need to know where the centroid is. The centroid is going to be 2 meters down on this plate. And so I guess, can you see this? If I draw it off to the side, this is drawing it in perspective. And this y sub c to the top of the surface is this. This is to the water surface. So this is y sub c to the centroid. And so we can use this. So we know that for a rectangular section, conveniently right here, the magnitude of this term is this. Standard result. B is the width, A is the depth. Has to be that way. And so we have to be careful to use that. So A is the depth cubed divided by 12. And so if we use that in here, then this is the term YC1, which is we've just calculated, which is going to be equal to 3 meters plus 4 meters divided in 2. So that's 5 meters again, hopefully. This is here. This is going to be a 12th width, 3 meters into the page, depth, 4 meters. This is 4 meters deep to the power 3. The depth of the centroid is the same here as it was before. And the area of the plate is 4 meters deep, 3 meters into the page. And so if we come up with that, we end up with a magnitude of 5.267 feet, which basically says that on this mock-up of the length here, this is 5 minus 3, because the height above here is 3. This is equal to 2.267 meters. Standard result for the horizontal one, it's always going to act. The centroid is the center of pressure, so it acts in the middle. And so we know that this length here on the bottom is 1 meter. which is equal to YR vertical, and this is equal to YR horizontal. And the rest of the calculation is just to do the sorry, let me correct that. This is not YR horizontal, is it? This is the lever arm, vertical. YR vertical is the full length up to the surface. Which is equal to 5.267 meters. Right? So this is the location where it acts. If we subtract off the 3, we've said that to be able to do this balance between a failure mode, we have to write it relative to the failing relative to this pivot. And so if we do that, then we have exactly this expression at the bottom, which is the horizontal force multiplied through by the lever arm, which is 5.267 feet meters minus 3 meters, which is the depth of this point, which is 2.67. So this is 2.267 meters. We have this vertical force, which is what we've called FV or FRV. And the lever arm here is 1 meter. So forget that, that's not right. And we know that this force here is being placed a total of 4 meters away from the pivot point. And so the only thing that we don't know is this. And we can solve for that. And if we do that, we end up with some number, which we may care about or may not care about. But basically, that number is the force that we have to apply at this point here to be able to stop it from opening up due to the horizontal push of the water and also the vertical weight of the water that acts as well. So that's just one way to do it. We have a few minutes left. Makes sense? Hopefully it makes sense. Yes? No? Hopefully? I should know never to ask that question. Just forge ahead. The other thing that there are more than... We could solve it in a variety of number of ways. And I don't know if I'll have enough time to do this. But in our particular geometry, what we did here relative to the water surface, the way we solved this was to you saw exactly what we did. We did this, and we did this, and we calculated what those overall forces were and where they acted, and we solved it by doing that. However, we could also, let's see if I can be smart enough to do this. Oh, that's fantastic. Can you imagine that? The skill. You could imagine solving it another way. I wasn't smart enough to actually do these erasures before I did this. Let me do this again, just to show you how clever I am. So I'm going to do it 3 different ways. Ooh, even lines it up. All right, so the idea is another way that we could do this would be to isolate a free body that looks like this. And if I did this, I don't want to confuse you, then the free body would be this force acting here, pressure distribution. the pressure acting on this upper surface, which would be equal to the water acting above it, and also the weight of water in this zone here. So in other words, if you defined the horizontal force acting here, the vertical force acting due to the water acting above this point, you'd get exactly the same result because it's physically the same system. You can see, I think, that this triangle here gives you exactly the same force acting in the same direction as you did in the previous one. And if you think about it, this weight of water plus the pressure that's acting on this surface here gives you the same force that would be acting due to this pressure at the bottom. So that the systems are both equivalent to each other. The third one, let me do it, and again I don't want to confuse matters, but just to make the point that you can solve these problems in a variety of different ways. The other way you could solve it would be by doing this. I really don't want to. And now the weight of the water acting downwards. And this would give you exactly the same result as well. In this case, we have this force acting here. We don't have any force acting here because it's got to come through the gate, but we have this force acting here. And so if you remove this force, because it's exactly equivalent to this force here, then you have a system which contains, if I outline this, the pressure acting on this side, which is the same as this. The weight of the force acting downwards here, which is this, and actually I drew this incorrectly, right? This shouldn't actually intersect this point at 0. It should have an offset in all of these. But the forces acting on this are exactly the same. And so the point is that you can choose a variety of different ways to be able to analyze your system. I'm pretty sure that this one that we chose for the main analysis is the easiest, but it's certainly not the only one that we could use. And so depending on the circumstance, each of these would give you identical results in terms of this force that would be acting that you'd have to apply due to P. It would come out the same in all cases. Okay. So I hope I didn't confuse things by that. There are multiple ways to do that. Okay, thanks very much.